Hey folks, welcome back to my combo classroom for a little bonus video where tonight I'd like to tell you about 3 different ways that you could derive or prove the formula for what are called triangular numbers. First, let me quickly note that I recently put out an episode about fractals and Pascal's triangle on my main combo class channel, and make sure you check that out at some point. It's linked in the description. And one of these 3 triangular proofs or derivations is something that I briefly showed on my combo class channel before, but I think that looking at all 3 of these will show an interesting sense of how some fundamental equations could be discovered or proved in multiple different seeming ways, and when you see several of them together, it can give you a more intuitive feeling for a concept like why the triangular numbers have a particular formula. Now, to start, triangular numbers are a particular type of figurate numbers with a triangular shape that follow a pattern of 1, although we could start with 0 being the 0th triangular number. That technically works with the formula we're going to look at, but let's begin with 1 to keep it simpler. We have 1, and then 1 plus 2, which is 3, and then 1 plus 2 plus 3, and etc. And in general, they have these little triangular shapes if you draw them, or you could phrase them as 1 plus all of the whole numbers up to some point we'll call n. Now, we also could write this using summation notation to say that we're summing all the numbers up through n, but writing it a different way isn't what we're looking for here. What we're looking for is some formula for what the nth triangular number ends up becoming, not just in another way of writing that we're adding up all the whole numbers to there, but is there some formula that's simpler that we could plug n into and know how many dots are in the nth triangular number, or what would that particular sum be? And if you haven't encountered this before, maybe pause the video briefly and see if you can think any methods of how you would come to that. But for now, we'll begin with the first of these 3 ways I want to show, which is the one that I briefly touched upon in my combo class channel. And the way this is going to work is by saying that the nth triangular number, which we'll call Tn, equals all of the numbers from 1 through n added up, whether we're writing it in an ascending order or writing it in a descending order. Where here, let's say we filled in a little more of what was going on and noted that before n, we get to n minus 2, n minus 1, and then n on the way there. And here, if we put that in the opposite order, writing it descending, that's another way that, since addition can have its terms scrambled without changing the result, it's obviously going to equal the same thing to just write it in a backwards order. Now, what we're going to do is try and sort of line these up. I don't have them very well lined up, but we can still imagine them corresponding, where the first is corresponded with the first there, the second is corresponded to, and then the second from top, 3, and then the third from top. And if we then add up these 2 lines, what we end up getting is that twice Tn equals, here we have n plus 1, here 2 paired with n minus 1 becomes n plus 1. Then 3 paired with n minus 2 becomes n plus 1. And all of the pairs become n plus 1. So we have n plus 1 lined up a certain amount of times, adding up that many n plus 1s, where the amount of them was n. We had that n times. And just like the written version of times, that we did it that many times, we can use times like multiplication to say it's n times n plus 1 must equal twice tn, meaning that if we just want 1 tn, we can divide by 2 here, get rid of that, and we have a formula. Tn is n times n plus 1 all over 2, which you could write a few different ways, by expanding that, by applying the denominator of 2 to things individually, or a variety of ways of writing it. But we're going to go with this relatively simple way of phrasing what Tn is and say, well, maybe you wouldn't have come across this on your own. Are there any other simple ways that you could have played around with numbers or even shapes and came to this exact same conclusion? Well, next, we're going to look at something that has a similar role of adding two TNs together, but visually. Let's take a particular triangular number. Let's say the fourth triangular number, and let's write it or draw it in a sort of smushed way, where we line up them almost like we had to put it on a square grid. And that does end up having a 1 plus 2 plus 3 plus 4, even if we skew the triangle a bit like that. And now let's, after putting a little triangle around it to make it clear which ones are part of that, let's add another of the same, another fourth triangular number. And well, if we tuck that to the side right here, we end up finding that two of the same triangular number end up forming this rectangle of dots together. And what are the dimensions of this rectangle? Well, it had n, 4 in this case, on one of its dimensions, and it had n plus 1 on another one of its dimensions. Although this isn't perfectly drawn, if you tried yourself with other triangular numbers, you would notice this pattern continuing, where I could draw a sort of smushed version of any triangular number and draw itself flipped in a way that turned their dots into a rectangular grid that would always end up having one dimension that was which triangular number I'm looking for, and one dimension that's one more than that. And so, what does that tell us? That twice Tn equals n times n plus 1. And once again, dividing by 2 gets us that same thing. Leave a comment if you can figure out a way that you would make this more rigorous, like how you would describe the way that we can know that this pattern continues to further cases. Well, one way that you can show that things extend to further cases is a proof technique called induction, and that's actually the third method that we're going to use to come to this same conclusion. For this induction-based proof, we have to assume that we already had a clue that maybe T of n equaled n times n plus 1 all over 2, but we wanted to prove it and verify that it really was true for all triangular numbers. Well, induction has two crucial steps. proving a base case and then proving that if a given case holds, the next one also does, which ends up causing sort of a domino effect chain reaction where the first case proves the second, which proves the third, and etc. And here that means we want to first prove that the first triangular number works for this. And all we have to do there is know that the first triangular number is 1, which is very easy to calculate. And then plug 1 into this and see 1 times 2 all divided by 2 does equal 1. So the first triangular number equaling 1 does work for this formula. And now we want to prove that if this formula is true for any given t of n, that it also must be true for the next triangular number, for t of n plus 1. And if we look at what it means for this to also be true for t of n plus 1, we could imagine substituting n plus 1 where there were n's here. That becomes n plus 1. This would become n plus 1, which is n plus 2, all over 2. And here, this is basically just showing the next version of this written out of what it would mean for this formula to still be true for the n plus 1 case. And so we're basically trying to now prove that if this was true, this would also be true. Now, what does it mean to go to the n plus 1th triangular number? Well, when we're up to here, t of n, that's 1 plus 2 plus 3 all the way up through n. So going to the next triangular number is taking that same thing, 1 plus 2 plus 3 up through n, and then now also adding an n plus 1 afterward. So we know that by definition, t of n plus 1 is t of n plus n plus 1. And here, if we look at this as an assumption, that we're trying to show that if it's true, this is also true, and we then take the n plus 1 we added on here and say, okay, instead of t of n plus 1, we'll say this assumption for t of n, that plus n plus 1 should be equal to t of n plus 1. And if we take this and expand and simplify things a bit, we could clump these with the numerators there. Well, let's just expand it over here and note that if we clump it all together, we have an n squared plus n plus, if we want these to be the numerator of this same fraction, we would make that 2n, because it's going to be over 2, plus 2, because all of that is going to be over 2 in this form. And then we can combine these like terms. We have an n and a 2n, so really that's plus 3n altogether. And what do you know? This numerator here, n squared plus 3n plus 2, can always be factored as n plus 1 times n plus 2. And we'd still have the over 2. And if you want to see that this is the factored form of that, you could just use the distributive property here and you'd get that. Now, what we've seen is that based on the definition of how t of n plus 1 builds upon t of n, if t of n had that formula we first had written, then we looked at the n plus 1 extension to it, it would end up having the formula we showed we were trying to prove is implied from that assumption. Meaning that altogether we've showed that if t of n has the formula of n times n plus 1 all over 2, then t of n plus 1 does fit in to its version of the exact same formula if we substituted those in, meaning that if any given triangular number matches this formula, the next triangular number must also. So, since the first one we easily demonstrated does fit the formula, the second one must also, which means the third one must also, and etc. If that's confusing at all, well, keep your eye open for other proofs by induction, which will show up here and there on my channels. Anyway, I hope these 3 different ways that somebody could discover or try to prove the formula for triangular numbers gave you a bit more of an intuitive sense of why this formula makes sense to describe the nth triangular number. I wanted to do this bonus video now because triangular numbers will be making many appearances during this grade of combo class, which is grade -3 that we're in. And like I mentioned earlier, make sure you're also tuned into my main combo class channel, where there are 2 main official episodes of the grade out so far. And I'll have more bonus content on this channel soon too. If you want even more bonus combo stuff or want to help me with making this grade, you could consider checking out the Patreon that's linked in the description or the YouTube memberships on this channel. And in any case, thanks so much for watching. I love you and I'll catch you again soon.